Saxon Advanced Math Lesson 46 is about complex roots. Now, a couple of things we have to remember about what complex roots are or what that means. Remember that the word complex doesn't just mean complicated like it does in the English language. Complex, usually what that's referring to is the square root of -1 or an imaginary number. First thing we need to remember about imaginary numbers is that the real number set can be written as a complex number, or always can be. All real numbers can be. And they have a complex part built into them. They just have that hidden. Kind of like if I just said x plus 2, what's the coefficient of x? Well, the number modifying x is an understood 1. We don't have to write it for it to be there. This is very similar to that. This allows me to write a complex root, a number. If I said the number 3, well, 3 isn't complex. There's no square root of -1 or no I in there. But if I put this in there, I can write it as 3 plus 0i. I'm showing the imaginary root that exists. That's the first thing to remember, that it's always there. So when we take the complex roots, that's complex numbers. Now, what are roots? Remember from a few lessons back, we have, if I said write a quadratic equation of roots of 2 and -1 with a leading coefficient of 1. What we would do is we would write that and we'd say, remember that x minus 2 and x minus a -3, and then we would put those in there and multiply that out. That negative makes it a positive, and when I do so, I end up with this, and that simplifies. -3 and -2 simplifies to 1x, and I end up with x squared plus x minus 6 equals 0. This is the quadratic equation, or quadratic form, I'm sorry, of this. And when I take this and factor this back, I end up with this right here equals 0, and these are the roots that I'm plugging in. That's just a little review on what we're going to be working with complex numbers as well. Look at example 46.1. Write the quadratic equation with a lead coefficient of 1 with the roots of 1 plus 2i and 1 minus 2i. Now, I'm skipping around a little bit. We'll go back to what the book says about some other terms in here, being that real and negative and conjugates, and we'll refer to that in a minute. But if we just take this here and realize that these are conjugates of each other, and when I multiply an object or a term by its conjugate, it cancels the second term out, whether that be a root or an I, because I times I is -1. I'm going to use the same method I did here with finding this equation by using the method of saying x minus and x minus, right? And so I did that with x minus and x minus, and I plugged in my first root here and my second root here. At this point, I'm ready to go ahead and simplify this wherever I can, and I have a -1. Now remember, this is key that you catch this. The negative gets distributed to both terms because there's an understood 1 in the front of this parentheses here, that when I distribute that -1 times 1, I end up with a -1. A -1 times 2i is a -2i. I do the same thing here and end up with it being x minus 1, x minus 2i, and x minus 1, x plus 2i. Now, I'm almost done, but I want to go ahead and multiply these out. This is where it's going to take a little bit of review for you. It's been a while since you, at least in this book, have taken a trinomial and multiplied it by a trinomial. And that's why I went ahead and wrote it again and put the first set of arrows on it. Sometimes people like to call this FOIL, but it's not really FOIL because you have two inners. And that gets to be confusing when you say first, outer, inner, last. So in other words, this one I like to call it left to right method because it makes more sense in my head. I start with the furthest most left variable, which in this case is x, and I distribute this x into all three of these terms. This one will get distributed into all three of these, and this one will be. That means a 3 times a 3 polynomial, so a trinomial times a trinomial, will always end up with 3 times 3 sets, which is going to give you 9 individual terms that you can later combine. Some of them will cancel and some won't. So when I say x times x, that gives me my x squared. X times -1, -x. X times 2i, and that gives me 2xi. -1 times x, -x. -1 times -1, +1. -2i times 2i, and that's going to give me a 4i. okay, squared. And that's what's going to be very careful with here, is because that's a negative 4i squared. What do we remember about I squareds? And that is I squared gives me a negative 1. And when I say a negative 1 times a positive or a negative 4 gives me the positive 4. Then I start combining my like terms. The x squared comes down. Negative x is a negative 2x. A positive 2xi and a negative 2xi. That's gone. And then I have a positive 1 and a positive 4. So that's a 5. And then I look at it and say 2i and negative 2i, and those are also going to cancel. So I end up, when I combine all my like terms, with just this equation, x squared minus 2x plus 5. This would be the factored version. This is the quadratic form. And then if I were to factor it, it would give me this again, or actually this one. So how would that work with this? Well, let's go ahead, and then the book doesn't really show you this, and I wanted to take just a minute to explain what we're doing. If I were to take this right here and tell you factor this, come up with the roots of this right here. Well, we know we could use completing the square, we could use the quadratic formula. I like the quadratic formula, so I went ahead and wrote it over here. And I started plugging in what I knew. A was 1, B is negative 2, and C is 5. And I plugged them into the quadratic formula right here. I start simplifying, and negative is a positive for the 2. Negative 2 squared is a positive 4. 4 times 5 is going to be 20. I've got a negative in the middle. 4 minus 20 is a negative 16. Now, if you're paying close attention here, I did put a positive 16 here because I realized that the root of negative 1 is I. And so I slid that out to the side here. So don't let that confuse you where that came from. So this, because instead of being a root of negative 16, it becomes the root of 16i. Now I look at this and say, well, 16 is reducible. Root of 16 is 4. And I pull out the 4 to the front, and I realize, oh, this has a 2, 2, and a 4, and that's going to reduce down, right? 2, 2, and 4. And that's going to give me two roots. X is equal to 1 plus 2i, and x is equal to 1 minus 2i. Do we recognize these? Yeah, that's our original problem. And which tells me that this is just the opposite, right? We're starting with the answer. They're saying here are the roots. Find the quadratic equation it goes with. Whereas before we had, here's the quadratic equation, find the roots. And that's what I went ahead and did here. Now, I want you to notice something, and the book slid this in without a whole lot of explanation, and that is that all quadratic equations with real number coefficients, these complex roots always occur in conjugate pairs. These are all real coefficients, which means that they are going to exist in conjugate pairs. Now, don't let that be confusing to you, because as you look at this, you think, well, I've factored lots of things that looked a lot like this and had both real roots. They did, but that's why we started with talking about this right here. See, the conjugate root of these, if this was the answer, was maybe the roots, like in this case here, are 2 and 3. This is 2 plus my hidden root, right? 2 plus 0i. And negative 3 minus 0i. It's a conjugate pair. They're hidden in there, and if we were to take the time to work it out, you would get the same answer back, because they always are existing in conjugate pairs. Now, these, and that's why these worked out, that when I took a conjugate pair, remember a conjugate means that the term in the middle is changing its sign, and when I multiply them together, it reduces it. And we've used conjugates to rationalize the roots of complex numbers or rational numbers. And so we've done that where we've moved that root out of the denominator. And normally we would do so by multiplying by the root over the root. But if we have 1 plus the root of x on the denominator, I can't do that. So I multiply the bottom and the top by 1 minus the root of x, because I know that a conjugate pair is going to cancel the middle terms and square the last term. That sounds really familiar, because that's what we did here. We canceled the middle terms and squared the last and ended up with a non-complex answer. So this is how you write it with complex roots. and you can do problems like this just by writing x minus, and then putting both sets of roots in, and then just multiplying. Remember, when you multiply, you're going to have 9 terms like I have here, and then combine your like terms. If you're doing it correctly and they're giving you a conjugate pair, all of your i's cancel out, whether that be by squaring them or by the fact that the i's cancel because they have opposite values that get canceled with them.